So power functions. You may have never heard these functions referred to as power functions, but you've definitely seen them. All right, so a power function is any function in the form of f of x equals a times x to the nth power. Right? So like 2x squared, that's a power function. And a cannot equal 0, because if a equals 0, then the whole thing equals 0, and it's not a power function. And then n can also not equal 0, because anything to the 0 power is what? 1, and then that would just be f of x equals a, which is a function. It is a monomial function, but it's not a power function, okay? Make sense? So it's not 2x squared plus 3. There's nothing else added on. It's just one term, which is called a monomial. So this goes on to say a power function is also a type of monomial function. We're going to draw a sketch of each of the following monomial functions, which for most of them, they're the parent functions we already know. Constant, this is f of x equals c, just some number. That means it's going to be a horizontal line. So it could be, c could be any real number, so we'll just make it that one right there. Linear, we know that that is f of x equals x. And my parent function just looks like this. We know what a quadratic looks like. F of x equals x squared. We know what a cubic looks like. F of x equals x cubed. Right? All that stuff so far, old business. We agree with that much? All right, so quartic and quintic, hopefully from the pattern here you can at least come up with the equations would be f of x would equal x to the what? 4th. And quintic, f of x equals x to the 5th. Okay? So without guessing, like you truly know, does anybody know what the parent function of a quartic would look like? It looks like a quadratic, okay? So, and it may or may not be something that you've done, but it basically looks like a quadratic. And without any kind of scale on my x and y axis, I mean, my little sketches could look identical. Looks like a quadratic. So then, what do you think a quintic would probably look like? A cubic, exactly. So if you have a power function, meaning, again, we're not shifting left, right, up, or down, nothing like that, but a power function, and it's just a monomial, anything that has an odd exponent is going to look like it have the shape of a cubic. Anything with an even exponent is going to have the shape of a quadratic. We start adding extra stuff on that, the graphs change drastically. So we're just talking basic monomial functions. Make sense? We good? All right. So if we look up here, the power function, for the power function, if the function has an even power, so that would be our quadratic and our quartic, basically, then it is symmetric about what? What are the even-powered ones symmetric to? The quadratic and the quartic, where's their line of symmetry? The y-axis, right? Aren't they just symmetric to the y-axis? Okay, so symmetric about the y-axis. For my odd-powered functions, the cubic, quintic, linear, so if the function has an odd power, it is symmetric about what? The origin, very good. So I'm using different wording. I'm saying symmetric about the y-axis and about the origin. That's the same as symmetric with respect to, or symmetric to, or something, you know, I'm just using the different wording so you know they all kind of mean the same thing. All right, we all good with all that so far? Awesome. So now let's look at what happens here with our in behavior. All right, we've talked about in behavior a lot. We're still going to talk about it a lot more. My in behavior, so if I have f of x equals x squared, or or x to the fourth, or x to the sixth. If I have an even power and a positive coefficient, then in general, my graph is going to look like a quadratic. So my end behavior, as x approaches infinity, what does f of x approach? Infinity. And as x approaches negative infinity, what does f of x approach? Infinity. Okay? If I still have that even power, x squared, x to the fourth, x to the sixth, but I have that negative leading coefficient, then that's just a reflection in the x-axis. So now it just flips down. My end behavior, as x approaches infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x approaches negative infinity. Very good. So my odd power positive coefficient, you would picture a cubic, right? And then that should help you with your end behavior. As x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x approaches negative infinity. Very good. So then still odd power but negative coefficient, that just makes it a reflection in the x-axis. As x approaches infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x approaches infinity, right? Okay, so that's like a piece of cake now, right? You can get that because that's going to be super important for what we're going to do when we start graphing stuff with this. Not necessarily the graphs we're doing today, but all right, so this says to graph each function and identify its key characteristics. So I have f of x equals 3x to the sixth. So I know that the x to the sixth parent function, sorry, I'm leaning on the board, looks something like this, right, in general. And then just like with the quadratic, I have 5 anchor points. Okay. Notice I'm not shifting this anywhere. No left, right, up, or down. What does that 3 do? Vertical stretch, okay? So I have a vertical stretch by 3. When I go to graph this here, I know that this is 0, 0, 1, negative 1, 1, 1, 1. But if I substitute in a negative 2, and I don't know, we didn't even talk about what the anchor points are, but this is f of x equals x to the sixth, negative 2 to the sixth power. Well, before we even do the math, if you don't just know what it is, that's going to be kind of a big number, right? Is it at least bigger than 10? Yes, and so since I know I'm not shifting my graph down, there's no way it's going to be on the grid. So I don't even really care what the number is. You with me? So then I'm going to go, so that one's just out. So then I go to negative 1, 1. Negative 1, 1. All I do is a vertical stretch of 3. Looks like that. 0, 0. My vertical stretch doesn't do anything. 1, and then 1 to the sixth is 1. So and then that's a vertical stretch of 3. Looks like that. But what I know, since it's x to the sixth, it started off skinnier, and when I do go to 2, it's going to be way up there. So this comes in pretty skinny to look like something like, well, a bit better than that. I did skinny on one side and on the other. Something kind of like that. Where we could make it look a little wider if we knew it was, but I'm not going to be too nitpicky about that stuff. We're not going to worry about filling in all that stuff over there because I know you can figure that stuff out. Let's just talk symmetry. It has symmetry about what? Y-axis. Very good. Any questions at this point? Awesome. All right, so let's look at the next one. This is negative 2x to the fifth. So my parent function is f of x equals x to the fifth, which I know has the same basic shape as a cubic. And just like the cubic, I have 5 anchor points. So my first anchor point is not negative 2, negative 8, because this isn't a cubic. It's negative 2 and whatever negative 2 to the fifth power would be. Again, is that going to be smaller than negative 10? Like, is it going to be way down here? Yeah, and I'm not shifting up, so it's not going to be on my graph, right? So I don't have to worry about it. So I'll just start with this negative 1, negative 1, negative 1. So that negative tells me I do what? Reflect in the x-axis. And then I have a vertical stretch of 2, so it becomes right there. 0, 0 is just 0, 0. Then 1, 1, I reflect in the x-axis, vertical stretch of 2. And again, I would make this really skinny because that's going to be a big number off my graph there. And it looks like that. And then this is symmetric about what? Origin. Any questions at all about the power functions or the monomial functions? Are we all good? All right, so then we're done with the blue paper. We don't need to do the last one. You got the gist of it, which is what I wanted. So grab the other one, and let's talk polynomials. Okay. Poly meaning many, nomial meaning terms, right? So many terms is what it means, or more than one at least. So it says a polynomial function is a function in this form, which looks hideously horrific, right? So it has to look like that because we have to generalize with variables. We can't use actual numbers because basically it's saying they can kind of be anything. So an example of a polynomial, just so we can talk about it as well, could be 3x to the fourth minus 2x cubed plus x squared plus 5x minus 2, something like that. Okay. Polynomial. So when you're factoring polynomials, you know what a polynomial looks like. So what this means, because, yeah, okay, this is a big mess, and as long as you know what a polynomial is, that's fine. But you also have to be able to look at these kinds of things and try to make sense out of them without it freaking you out so you can actually understand some of the rules and stuff moving forward. So I have a sub n, and it says the coefficients are the a's. So a sub n for this one is 3, right? And this is x to the n power, so n is 4. So when I go to a sub n minus 1, that's a sub 3, which would be the negative 2, and then x to the third power, and so forth and so on. And then it's dot, dot, dot until you get to a sub 0 with no x on it, because it could be an infinite amount of terms. In this case, I only have 5. Okay, but do you see how that kind of explains polynomials in general, right? That's what I want to make sure you can see that here. All right. And n has to be a positive integer. I mean, that's what, no negative exponents. So shape and continuity, what you need to know about polynomials, which is going to be helpful in some cases to know the true, basically the true definition, is that polynomials are smooth curves with no breaks. So if I put my pencil down on the far left side of it and I sketch or I trace over my polynomial, I'm not picking my pencil up. So if there's no breaks, it means it's not discontinuous. So it is continuous for all real numbers. All polynomials are continuous. So if we have something that's not continuous, it's not a polynomial. It's still a function, it's still an equation, but it's not technically a polynomial. Okay, easy enough? Then the degree. The degree of the polynomial is the highest, not the first, but the highest exponent. If it's written correctly, like in true form, it should be the first, but don't always just pick the first. It's the highest exponent you have. So it's the highest exponent n, and that is the degree. Ooh, if I can spell degree. Polynomials are classified by degree. So this one that I wrote up here, my highest exponent is 4, so n is 4. So that would be a 4th degree polynomial. That's how we would talk about it. That's how it's classified. But they also have names that go with them, which we'll look at here in just a second. But just calling it 4th degree is fine as well. So we're going to identify the degree for each one of these and classify it. So we're going to start from the bottom. These are all in order from greatest to least for the exponents, which is great, but always double check that just because there's a 5 here, if there was a 6 here, then 6 is the highest number. But so my degree here is 5. The degree here for this one is 4. I don't care about the coefficients or anything else. This degree is 3. This degree is 2. What do you think this one is? 1, because we don't see the 1, we don't put it, but there's technically like an invisible 1 there, right? So what would this degree be? 0, because if I did have it on there, it would be x to the 0 power, right? And then it would just, x, anything to the 0 power is 1. Okay, we good with that? So we're going to classify these. When you have just a number, then it doesn't vary. There's no variables. This is a constant function. To the first power, that's linear. To the second power, we know that's quadratic. To the third power is called what? Cubic. What's the fourth power called? Quartic. 4 quarts in a gallon, right? Quartic. 5, quintic. But it's fine also to call it a 5th degree, 4th degree, whatever, just because there's names past that, but we don't need to get all crazy and fancy or anything. Okay, so now we're going to talk about end behavior again. It looks almost identical to what we did on the other paper, but it's a little different because these are not just power functions. Okay, we're talking now about polynomials. So it says the power and coefficient of the leading term determines the end behavior of the function. So we're going to recall from the power functions that if I have f of x equals x squared, I know that it looks like this, and I can figure out the end behavior. But if I have, this just says even power positive coefficient. So for a polynomial, because this is not a polynomial, my polynomial could be f of x equals 3x to the 4th plus 2x squared minus 1. Right? So let's say I have that. That does not look like a quadratic. Okay? That's going to look like something else that you don't know what it is right now, and that's okay. But what you do know is what the end behavior is. Because when I look at this, this is an even-powered function and my positive leading coefficient. So no matter what's going on in the middle, I don't care because this is end behavior. We'll worry about the middle tomorrow. Okay, this is end behavior. The end behavior of this looks identical to this end behavior, which is right here. So it's just up, up. Okay? Now, the words are still important. You know, as x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x approaches infinity. But for what we're going to use this for, we also need to think about it just this. It's just up, up. Okay? That's all that's happening, and that's what I can figure out from that. Okay? We good on that? So then if I have an even power negative coefficient, maybe I have f of x equals negative 3x to the 6th plus 4x to the 4th, and let's just leave it like that, it doesn't matter. But so I have a even power, x to the 6th, negative leading coefficient, so that negative, just like here, is going to reflect it down. Again, the middle does not look the same, but the end behavior does look the same. So since it's even and negative, my end behavior is down, down. We'll worry about the middle later. Odd power positive coefficient, so f of x equals 4x to the 5th minus 6x squared. Totally does not look like that picture over there. But I do have a positive coefficient and an odd exponent. Therefore, the end behavior looks the same, which is down, up. Same end behavior as a cubic. Then I have, so then odd power negative coefficient, so like f of x equals negative 2x to the 7th plus 3x squared, whatever. Then again, middle behavior looks different. However, end behavior would look the same as this, so that is up, down. So odd is opposite. Odd is opposite. Even is same. It's either up, up, or down, down. So if I gave you something that looked like this, let's say I gave you a picture and it looked like this. Okay. Then I do not expect at this point for you to tell me what this equation would look like or much more than that, especially because there's no numbers or anything on here. But you should be able to tell me, if I was to write this equation, is the leading coefficient positive or negative? Positive. And is the degree even or odd? Even, because it's up, up, right? So then if I gave you something that looked like this, is the leading coefficient positive or negative? Negative. And is the power even or odd? Odd. See how you can figure that out from the graph? Because that's going to be important pieces of what we need going forward. The middle, that's something else we'll talk about tomorrow. We're just talking about end right now. We good? All right, so let's flip it over on the back. So using the leading term, we're going to give the end behavior of each polynomial. So we're also going to talk about what it is. So this is x to the fourth. So it's a fourth degree, but what do we call it? It has a fancy name. What is it? Quartic. Good. Quartic. All right. And then it's even, so it's either up, up, or down, down. Which one is it? Down, down, because that's a negative, so it got reflected, so it is down, down. Make sense? All right, what is number 2 called? Quintic. And so that's even or odd? Odd. So it's opposite. So if it helps you, draw yourself a quadratic and draw yourself a cubic so you have something to refer to. And so then the end behavior here, is it down, up, or up, down? Up, down, because it's opposite of that. Very good. We okay with that? All right, you do 3 and 4. Okay. Kylie, give me number 3. What's it called? Quadratic. Quadratic. And what does the end behavior look like? Up, up. Y'all agree with that? Yes. Thank you, Kylie. All right. Nyla, what do you think number 4 might be called? Because it's not on that list, but tell me what you think it might be. It's okay. It's one you might not know. Swazi, you want to help her out? Septic, that's one option. Are you in French? Or you just know your prefixes? Anybody in French? Nobody takes French? We have French classes. Nobody's in it? Okay. So there's actually 2 options. So septic, because the prefix sept does mean 7. There's another one, though. Like when we talk about polygons in geometry, a 7-sided polygon is not a septagon. Do you know what it is? It's a heptagon. Very good. So septic or heptic, and they both mean 7. All right, so Nyla, back to you then. What does the end behavior look like? Is that leading term, does it have an even or odd exponent? Odd. So it's going to have to look like this. Then you have to decide if it's this or this reflected. So would it be down, up, or up, down? Down, up. Very good. All right, what questions we got? Good enough? All right, so we're going to skip number 5 and 6. Let's look at numbers 7 and 8. So on 7, it says describe both the power and the coefficient of the leading term. So when I look at number 7, is that going to be an even or odd exponent? Odd. So we have an odd power And would the leading coefficient be positive or negative? Negative. Any questions about how we know that or anything? We're good? All right, then you do number 8, and I'm going to get somebody to help me. Okay, Devin, is this even or odd? Even, very good. And then Ashley, is it positive or negative coefficient? Positive, very good. Any questions about either one of those? Very good. Okay, so let's talk about turning points. So our turning points, they're the points at which it switches direction. They're also our maximums and minimums, right? It's where we change from increasing to decreasing and vice versa. So if you have a turning point that's higher than any other nearby point, remember we talked about the points in its neighborhood, then that makes it a relative maximum. Which would be like this point right here. If the turning point is lower than any nearby point, then it is a relative minimum. So hopefully that sounds familiar. So we've talked about that. But I want to make sure I make something clear because I don't know that I made it clear the first time. So this will be my relative minimum. If I had a picture that looked like, I don't know, something like that, right? Then how many relative minimums are there? There's 3. How many absolute minimums are there? 1. So this is an absolute. You can only have one absolute. This is the absolute minimum. All 3 of these are relative minimums. So even though this is absolute, it's also relative because if I only have this piece, that's all I can see. And I don't know if I made it clear before that when it's absolute, it's also relative. So I just want to make sure that you do understand that. So our maximum and minimum values are called critical points, but there's a subcategory of that. What's that? Do you remember? There are maximums and minimums. They're extreme values. So what do we say for plural? Extrema. Yes. Okay, good. Extrema. And then the turning points define where the function is increasing or decreasing. So we've kind of already talked about that. I just wanted to clarify, the relative part of that. So this next part says, use the calculator to find the turning points. No, we are not, for a couple of reasons. First of all, I'm not putting a calculator in your hand. Second of all, for us to do this on the calculator, you literally have to just learn which buttons to push, and it gives you a number, and you have no idea why or what it means. So all that really matters right now is that you understand what they are and basically where they are and what they do. Because the math behind actually finding them is calculus. That's why we would have to use the calculator, and it's really kind of pointless because it doesn't help you learn anything. Okay, we good? Awesome. So your assignment is on Delta Math.